introduction. So as he said, I'm going to start the multi-core and more session off immediately with the and more part. So I'm going to be talking about our work on targeting reconfigurable architectures from higher level languages. So to start off with, I'm just going to briefly put on my computer architecture hat just to motivate our discussion. So we're all familiar with, of course, instruction-based processing, where we have some fixed CPU or GPU architecture, and we have some stream of instructions. And we're executing this through time. Now, unfortunately, these instructions that we know and love come with some overheads. So if you look at the energy required to do an integer add, for example, that takes about 0.5 picojoules, or at least it did in 2014. But the total cost of executing this entire instruction is about 70 picojoules, so about 140x energy overhead just to do the instruction fetch and all of those extra control overheads for administrating the execution of your operation. So this has actually become a problem in recent years as we see that CPUs are hitting this power wall, where essentially, even if we can add more and more transistors to the chip, we can't feed power into it without burning the chip up. So the end result of this for application developers is the performance improvements they've gotten from generation of chip to generation of chip that they see just inherent in the peak performance available in the architecture has been slowing to a crawl compared to what they're used to. So if you're an architect presenting this slide, as many of them do, at this point you would say, well, now it's time for specialization. So let's look at specialization. So one of the most extreme things you can do to get rid of the instruction overheads is to get rid of instructions. So you can take your program and lay it out in space, connect all of the operations together with wires, and add some custom scratch pads to hold your data structures. And this is essentially the way that you make an ASIC, modulo some additional hardware development stuff. But as we know, ASICs have fairly, and this is what I'll be calling configuration-based execution rather than instruction-based. So executing in space rather than in time. But as we know, ASIC development is rather expensive. We don't want to make a new chip every time we want to make a new application or put out a patch for a new application. So if we look at the available architectures today and just plot them in terms of the energy efficiency that they're capable of, because when you're power limited, really the only thing you can do to get better performance is decrease your amount of energy that you take per operation. The closest things that we can get to ASICs are coarse-grained reconfigurable architectures and field programmable gate arrays, or FPGAs. Now, so what is seeming likely to happen in the near future is, as we are needing more and more performance, we're going to be moving to these architectures that are programming in space rather than in time to get better performance. And this transition is actually already happening in industry. So you see companies like Baidu and Microsoft are moving to FPGA implementations. So Bing, for example, is being accelerated in their data centers in Microsoft right now using FPGAs. But one of the key problems right now, as you see here, I've plotted on the x-axis, not programmable, so ASICs, it's very difficult to program them, or basically impossible, to more programmable. So typically, FPGAs are rather difficult to program. So the key question that we wanted to answer in this work is how can we more productively target reconfigurable architectures like FPGAs when we're creating application accelerators to get better performance and better energy efficiency. So there's actually three characteristics that we really care about here. There's the performance that we're able to achieve with our design, so how fast and efficient are designs. There's the productivity, essentially how fast and efficient are our programmers. And there's the portability, how many different architectures can you target from a single source. So if we take a step back and look at the languages that exist in the world today, now there's a lot of different ways that we can classify these languages. I'm going to wave my hands and just use two. We can look at domain specificity, so the kinds of things that you can express within your language well, ranking from general purpose languages to domain-specific languages. And we can rank them in terms of higher level of abstraction, so very far away from the architecture, to a very low level, close to the architecture. And if we, so another way of thinking about this is sort of the declarative way of saying, what are you doing versus how are you doing it? So if you look at instruction-based processors, so like CPUs, for example, there's been a whole lot of work in doing basically a trade-off curve between low-level implementations all the way up to high-level implementations that are domain-specific. So this is really great. We have a lot of things to choose from based on how performant we want our applications to be. Now, if we take the same graph, and now we're plotting higher level to lower level on the left for reconfigurable architectures, what we see is the majority of our languages are down near the how. There's almost no languages up, or really no languages at all, above anything that looks more like C, or roughly a C-level abstraction. So essentially, this is the hardware description languages, or HDLs. The one other one that I didn't plot on here yet is high-level synthesis tools that are commercially available. So essentially, the idea of high-level synthesis tools that exist today is that you take a C program and you try and target it to hardware. Now, this is generally an undecidable problem if you want to get good performance. So what we do in current high-level synthesis is add a whole bunch of additional hardware pragmas about how to actually target your C program to hardware. So you're doing a lot of additional hardware optimization in C. And this essentially allows it to move over to a abstract-ish representation of hardware-ish. So if we now go back and take a look at those three characteristics that I talked about, we can first look at HDLs. So looking at the performance, portability, and the productivity. So obviously HDLs are very good for performance because we can do arbitrary optimizations manually from when we're creating application accelerators. They're not terribly portable. They have a lot of target-specific code, and they're not productive at all. So you're talking about things, instead of loops and data structures, you're talking about things that are state machines and register transfers. If we look at existing high-level synthesis tools today, so the C plus Pragmas approach, the performance that you can get is rather limited. So, for example, high-level synthesis can't support arbitrarily nested pipelining very well, or really at all. And this means that you can't really exploit the nested parallelism that's inherent in a lot of these applications. You can have some portability for a single vendor. So for Xilinx devices, for example, you can port your source from one Xilinx FPGA to another. But new architectures, say coarse-grained reconfigurable architectures, you can't target at all because these are proprietary tools. And the productivity is better. So we are introducing some software abstractions, so things like nested loops. But you have this strange ad hoc mix of software abstractions and hardware abstractions within a single language that makes it difficult to optimize, either manually or automatically within a compiler. So what can we do from here? Well, there's really no reason why we need to have high-level synthesis designed in C. We could actually go and implement a new language from the ground up, which is dedicated specifically for an abstract hardware representation. So if we look at some of the requirements for this, and I'll keep a score on the right for what C plus Pragma's approaches can currently do, we would like to have this new language represent our memory hierarchy explicitly. So whereas C represents your memory essentially as a uniform memory, because that's what the cache looks like, it gives you on CPUs, you have scratch pads and discrete memories on FPGAs and CGRAs. So we'd like to present this explicitly within the language. This allows us to do various memory optimizations within the compiler and designated manually. So we would like to express control as nested loops. This is something that C plus Pragmas gets right. The key thing here is that when you're doing static compiler analysis, loops are giving you loop iterators, which is one of the few things that are actually predictable in an otherwise random world. So this allows us to do things like memory optimizations based on access patterns. We want to be able to support arbitrarily nested pipelining. As I mentioned, C plus Pragmas currently can't do this, but this would allow us to exploit nested parallelism and get better performance. We want to specialize our memory transfers, specifically from on-chip to off-chip, to improve our DRAM bandwidth utilization. And we specifically want to specialize them based on the type of access patterns that we're doing, so whether you're doing a scatter or gather or a dense load or store. We want to capture design parameters. So in hardware designs, you have a lot of different things that you can change that you wouldn't necessarily think about in a software representation. And if we can capture these and give them to the compiler, we can automatically tune them so that the designer doesn't have to think about them a whole lot. And I'm just going to briefly talk about what that means. So that example that I showed in the beginning was actually a really simple implementation of a dot product in hardware. But we can do a couple of things to make it better. So for example, we can increase the amount of on-chip memory that we have to improve our DRAM bandwidth utilization, but this has some area cost. We can pipeline, so in this case, this looks like prefetching. We can overlap the fetch of the DRAM, from DRAM to on-chip memory with the computation of the dot product. Again, good for runtime, but bad for area. We can parallelize, so we can duplicate the amount of computation that we're doing. So we're doing multiple elements in parallel. Essentially, you're talking about a reduction when you're talking about a dot product, so we just turn this into a reduction tree. Again, good for runtime, not as good for area. And one other point to note here is that in order to feed the parallelized computation that we've created, we would then need to partition our memory so that we can actually have additional on-chip memory bandwidth to feed them. This is something you don't have to think about virtually at all with CPUs, but when you're talking about hardware implementations, this is something you need to be cognizant of in order to be able to deliver data to your compute. Okay, so if we go back and look at these criteria, what this allows us to get, again, looking at these three different metrics, we can get better performance, not quite approaching what we could get by manual implementations in HDLs, but better than what we could do with existing high-level synthesis tools. We can create a target generic source, which is essentially generic across any reconfigurable architecture, FPGA or CGRA. And we can be productive. So we can express nested loops for the programmer's productivity, but we can also do automatic optimizations like that memory partitioning that I showed you. And we can do automated design tuning using those sorts of parameters that I previously mentioned. So what we can do now is we can go back to this hardware, this taxonomy, and we can add in the new language. So we've implemented these requirements in a new language that we're calling Spatial. So I don't have a whole lot of time to talk about Spatial in detail, but I just want to go over a couple of the things that we have in Spatial and talk about how it meets these requirements. So first of all, I mentioned the memory hierarchy. So there's three main levels of memory hierarchy that we're concerned with on the FPGAs. So we explicitly declare arrays based on where they're going to be living within this memory hierarchy. So DRAMs are actually declared as DRAMs. Things that are living in on-chip buffers are declared as either SRAMs or FIFOs. These are actually going to be living in the scratch pads on the FPGA. And we have explicit transfers between them, which are specialized based on the type of access that you're doing. So whether it's a dense burst or a sparse gather. And finally, we have a representation of the registers within the FPGA as well. So if we look at the control and the way that we express design parameters in Spatial, we have sort of a mix between imperative and functional language design, since this seems to be the best way to capture a lot of the things that we want to do, like the parallelization. So we can, for example, have a reduction, which has an explicit parallelization factor. Which in this case, I'm saying it's default of 16, but it can be anywhere between 1 to 32. The compiler is allowed to tune it. And this parallelization factor can also be inferred automatically by the compiler. We have an implicit and explicit control scheme, so by default, the compiler will attempt to pipeline our loops, but if we want to override that behavior, we can add additional pragmas there. But by default, we'll try and do the best thing possible. Also, unlike existing high-level synthesis tools, which will only try to do that optimization if you tell it to with that additional pragma. So I mentioned the tile size before, so we can have this as a parameter. So this is essentially saying that we have a parameterized size for our array that lives on-chip memory that the compiler is allowed to tune. This is especially useful when we're doing tiled computation, as is often the case on FPGAs. And as I mentioned before, we can do this implicit memory banking. So if you're doing a parallelized access to a local memory, we can figure out how to do that automatically for you and bank it. So if you look at how we implement dot product in Spatial, just as a simple example, I have a declaration of the arbitrarily large vectors living in off-chip memory, along with some memory mapped register that's going to be collecting the output value of the dot product. We have a specification that's explicitly saying what part of our computation is going to be living on the FPGA. And then we're going to be expressing our dot product as a reduction. In this case, we're tiling the reduction in order to do chunking, so that we can bring in chunks that can fit on the FPGA and operate on them. So here we have declared the on-chip memories, as I showed, the local buffers that will contain chunks of the vector, along with an accumulator, which will contain the intermediate result. We have these explicit loads going from off-chip to on-chip. And then we actually do the inner dot product, so the actual implementation of the dot product on the FPGA, along with, since it's a tiled dot product, the accumulation to the actual output. And what you get with this, along with this higher level representation of a hardware implementation of dot product, is all these parameters that I mentioned. So you get the parallelization factors of the loops and the loads for free. You get this tile size that you've specified, and you get this banking strategy. So what we can do then is take this dot product and put it through a compiler stack. I don't have a whole lot of time to talk about the compiler stack, unfortunately. But I'm just going to highlight a couple of small things. So first, we do control scheduling. This essentially looks like a more general case of software pipelining that you might be familiar with. And the key here is that we can support arbitrarily nested pipelines. This is something that commercial high-level synthesis tools can't do. This local memory analysis that I mentioned, one key insight from previous work is that you can use the polyhedral model to do this when you're analyzing access patterns within a single loop. So usually you have access patterns across loops. And this is Spatial's contribution, is to do a near optimal banking and buffering strategy across all the loops in your entire program for your data structures. So in a nutshell, essentially you bank each reader as a separate coherent copy, and then you merge copies together. The paper has more details about this. We do automated design tuning. The original approach was to do simple heuristics pruning followed by random search. In the paper, we propose using a reinforcement learning method in order to do guided search of the space using a tool called Hypermapper. Again, there's more details in the paper, and if you're interested, you can come and talk to me afterwards about it. But a key here is that we don't have any transformations in the inner loop of our design space exploration, so we can do search quite fast. I'm going to skip the rest and just conclude with, finally, in code generation, we generate synthesizable chisel for the FPGA and some C++ code for host administration on the CPU, and anything else you don't want to run on the FPGA. So just to quickly evaluate Spatial, we took an Amazon Cloud instance, a single VU9P, fixed the clock rate at 150 megahertz, and compared hand-designed implementations in SDAccel, a leading existing high-level synthesis tool by Xilinx, that's based in C, and compared this to handwritten but automatically tuned implementations in Spatial. And what we see is, for the benchmarks that we evaluated, we see between a 1.3 to 14.1 improvement with an average of 2.9x. So the key advantages that we have here, if you look into it, are essentially our ability to do nested pipelining and our specialization of our memory controllers. Now, in terms of productivity, lines of code isn't a terribly good metric. User studies would be better. But on average, if we just looked at lines of code, we're about 40% shorter than what you have in terms of SDAccel for the same applications. And the main thing here is just our higher level representation of the memory hierarchy and the memory transfers. So lastly, I just wanted to mention our ability to port the same source in Spatial to different FPGA targets. So I'm going to go with that same Amazon VU9 FPGA again, and compare that to a much smaller ZC706 FPGA from the exact same source, but tuned automatically. So what you see is the bandwidth improvement that you get just by moving from one FPGA to another is about 4.5x, and moving from the exact same design from one FPGA to another, you see this improvement roughly. So Query 6, for example, which is bandwidth bound, has an improvement of about 4.5, 4.6x. Now, if we do automated design tuning on top of this, take this design and try and use as much compute and memory resources as possible on this new larger FPGA, we see an improvement between 1 and 9.4x for these benchmarks. The 1 comes from Smith-Waterman, which actually didn't have any design parameters at all. So this was just the way that the application was written. And the highest one, Black-Scholes, is a heavily compute-bound benchmark, which essentially we can just parallelize a lot to use the compute capacity better. So one other case, so by the way, for a user, what they'll actually see transparently from their single source if they move from one to another is the product of these two things. So the advantage you get from the FPGA itself and the advantage you get from automatic tuning. So one other case study we did is in our group, we're also doing architecture development, so coarse-grained reconfigurable architecture development. These don't look a whole lot like FPGAs, but they are still reconfigurable architectures. And we can use Spatial to target them as well. So the point that I wanted to make here was just that for compute-bound benchmarks, we maximize this PCU, or the compute resources on the CGRA. And for streaming or bandwidth-bound benchmarks, we're maximizing our DRAM bandwidth. So with that, I want to conclude and just say that reconfigurable architectures are becoming a key for performance and energy efficiency sometime soon, especially for applications where we really care about getting good performance. But the current programming solutions that we have for these reconfigurables are still rather inadequate. We want to have better productivity, especially as they become more prevalent. So we really need to think outside of the C box for high-level synthesis and come up with some new language techniques for doing this. And Spatial is our first prototype for this, implementing these language criteria that I mentioned. So from this, we can get a 2.9x speed up right now versus SDAccel, with 40% less code and this transparent portability through internal design tuning. So with that, I just want to say that Spatial is open source. If you'd like to try it out, it's at spatial.stanford.edu, and I can take any questions.
Thanks for the talk. Suppose I were somebody at Xilinx building like SDAccel, and I really wanted to stay using C. I'm prepared to use Pragmas and attributes and so on. Could I, to what extent can I sort of bring in ideas from Spatial, but in staying within C? What sort of speed ups might I be able to get using your work?
Yeah, no, that's a good question. As I mentioned, the key advantages that we're having is this memory controller specialization and the nested pipelining. So if you were to bring in all of these ideas into the high-level synthesis, if you still wanted to base it in C, I would expect the improvement to be somewhere around this improvement. So it's really all about getting the information. And in Spatial, we're trying to do this in the nicest way possible. But if you'd like to implement that using Pragmas in C, that's also another way of doing it.
So given the fact that Spatial outputs the chisel code, then I can imagine that it can be applied to ASIC design. So what do you think about that direction?
Yeah, so we actually are working on that. We don't really have any data for it yet. ASIC design actually turns out to be a little bit harder than FPGA design in general. There's more things that you have to do, but it is an area that we're pursuing.
Good work and good talk. So I was wondering about the data mapping to the specific hardware itself. Is there some way to synthesize or try out the different variants so that you can give hints to the programmer or see which is better?
Sorry, I think I missed the first part of that question.
So you're mapping data to specific hardware, right? SRAM or DRAM or registers. Is there some way to play around with different configurations and see which performs better or try to automate that?
Yeah, no, that's a good question. So at the end of the day, you do need to bring it onto on-chip memory in order to process it. But so one of the things that I didn't have time to talk about is that we can actually do optimizations of when you're specifying an SRAM, exactly what kind of memory you mean when you say SRAM. So there's various kinds of scratch pads depending on which FPGA you're talking about. But at the end of the day, you do need to bring something onto on-chip memory, and the tile size parameter is effectively what helps you out with that, along with our automatic tuning of which memory you actually mean when you say SRAM.
Hi there, I'm Adrian Sampson from Cornell. One thing I didn't quite catch about the arbitrarily nested pipelining is if that's something that shows up in the source code, and if so, how, or if it's a transparent optimization.
Yeah, so if you're coming from higher level languages, for example, so like a domain-specific language, you have a lot of information about the nested parallelism that you have inherent in the application. So if you're doing a nested series of loops, all of which you know to be parallelizable. What you can do is actually implement this as a nested series of pipelines in hardware in order to get the maximum amount of overlapping of your compute possible. So this is a property that's inherent in the application, which we can either get from higher level languages, bringing them down into Spatial, or you can specify manually in Spatial, as I showed with this, the reduction. And there's another one, I don't know if it was in a slide, but we have for each and a couple of other ones with inherent parallelism.
Thanks.
Hey, Dietrich from Cornell. Maybe I missed this, but how does when you port a piece of code onto another FPGA, how does this compare to hand optimizing for that FPGA in particular?
Yeah, so that's actually a hard study to do because it's difficult to find or make implementations that are hand optimized. But from what we've looked at, so for example, we've looked at ResNet 50 implemented on an FPGA through Spatial, and we've compared this to a hand-tuned design. I think what we see is about a 2x gap. And part of that is just some manual implementation, human creativity, basically.
Thank you.
We can take a last question while the next speaker is
Cousin
setting
from
up.
Rutgers. I have a question about your talk for that part, that for the first slide, for the motivational slide that you were talking about instructions like fetch and execute cycle. It reminds me of the extensible processors where you have custom instructions and those. So because you're talking about portability, do you have any support for those kind of processors that you could sort of map it to a new instruction or?
So the short answer is no, not yet, but we could add it. Right now we assume that there's a host CPU that lives off-chip. But you could bring one onto on-chip FPGA if you want, but we usually don't just because this is expensive in terms of taking up resources. So you'd rather use some off-chip CPU instead.
Okay, thank you.
Okay. Thank you.